Okay. So maybe we'll start. Yeah, it does work. Okay. So I just want to say my name is Priya Natarajan, for those of you who don't know who I am. I happen to have had the good fortune of being Angelo's thesis advisor, and I'm absolutely delighted to introduce him at his public talk today. Angelo arrived at Yale after a stellar record at UC Berkeley, and we worked very hard to recruit him, and I was very, very excited to have him work with me, starting off with his first theory project. And his interests were very clear. From when he arrived, he knew he wanted to work on supermassive black holes. And I think he's done wonderful work in his thesis, trying to learn a lot of different tools and skills and ways to think. And I've been very pleased with how open he has been to learning new ways of thinking about problems. And I think it would be fair to say that he's definitely been one of my star students whom I have often asked to stop working, not work so hard, take a break, go on a vacation, take a holiday. But at any rate, he kept at it, partly because he's very, very excited about what he does and excited about astronomy in general. And what I'm also particularly proud about is that he has been very, very committed to the public dissemination of science and has been very active at the Leitner Planetarium. So he's been a linchpin for our programs there, especially with the schools. So he will be really missed in the department, both at the planetarium, and I, of course, will miss him tremendously in my research group. And I want to say welcome to the Ricarte family, who's flown in from California to be here.
Thank you.
So thanks. We had fun with your kid for the last 6 years. And we're ready to set him off. And very happy that he's moving on to a very, very nice postdoc at Harvard. And I wanted to give him like a bit of a spoof gift, right? So those of you who know Angelo know that he's always to be found with his tea mug in his hand, right? So he would come to all the meetings in my office or our group meetings with, and the tea mugs got, better and better in quality. So first they were just tea bag mugs, and then later there were these like contraptions where you put the tea leaves, and he'd be carrying them along. And so I couldn't resist but get him a little spoof gift of 6 teas of the world for your next adventure. But at any rate, so here we
Perfect. Yay.
So here we are at the concluding part of the official Yale Astronomy Department PhD program, which is a public talk that our graduate students have to give. He passed with flying colors. He had his actual official qualifying exam. So I would like to, without any further ado, invite Dr. Angelo Ricarte.
Thank you so much, Priya. It is my pleasure to tell you about the work that I've been doing for the past 6 years here under Priya's mentorship on the assembly of supermassive black holes, which can be found at the centers of galaxies, from the seeding epoch near the beginning of the universe to the present day, 13.8 billion years later. To set the stage, we need to talk about our conceptions of space and time. Usually, as we go through our daily lives, it's convenient to think about just having a fixed grid in which you can move forward, backward, left, right, and up and down, and then maybe a separate time coordinate that you can look at your clock to check. But Einstein's greatest insight was general relativity. And this was the idea that space is not a fixed grid, and it's also not separate from time. Rather, there's this bendable fabric that we call space-time. And massive objects like the Earth, or even like ourselves, will bend the fabric of space-time around themselves, and that's how gravity manifests. There isn't some like invisible tether that's pulling the moon to the Earth, but rather the Earth has warped the space around it, and the moon thinks it's going in a straight line as it moves around, but because space is so warped, that straight line bends around and comes back to the beginning, and that's a closed orbit. If you bend space-time enough, you don't get just this little groove, you'll end up with a black hole. And this is an object whose escape velocity is the speed of light. And since nothing can go faster than the speed of light in the universe, that's a cosmic speed limit, nothing can escape past that region that we call the event horizon. Not even light. That's why we call them black. And observationally, astronomers have known that these are actually real objects that you can find. They're pretty tricky to find, but we found some. And there are two categories. So there's the stellar mass black holes that go up to 100 solar masses. You can find them via the gravitational influence in binaries, and very recently also in gravitational waves when two of them merge together. And then there's the supermassive kind, which I care more about. These go up to tens of billions of times the mass of the Sun, and those are at the centers of galaxies. And this is the very first year that we can replace this simulated image of a black hole with this real one. This is the one taken by the Event Horizon Telescope collaboration using a technique called very long baseline interferometry in millimeter wavelengths. And what you're looking at is that image before. That black region is the image of the event horizon. And the orange stuff around it is a bunch of swirling gas that's emitting millimeter wavelength radiation. So this black hole here has a mass of 6.5 billion times the mass of the Sun. So this is one of the ways that you can find them, looking at the light that's radiated by the stuff that's around them. If there weren't any gas going into this black hole, you wouldn't be able to make an image like this. Another way is to look at the gravitational influence of the black hole on its surroundings. And the best example is at the center of our Milky Way galaxy. There's a radio point source called Sagittarius A star, or Sag A star, and some people have spent their careers pointing at the galactic center and just tracking the motions of these stars from year to year. So this starts in 1995. And Andrea Ghez, in particular, at the UCLA Galactic Center Group, has been the one to take this data and create this video using the actual motions of stars. That yellow one in the middle had passed closest approach last year, moving at 3% the speed of light. That is a lot of momentum. And by analyzing those orbits, by seeing how quickly these are moving, you can infer for the astronomers using Kepler's third law that whatever invisible object is in the middle has a mass of 4 million times the mass of the Sun. And yet we've known about these objects for a few decades, but there are still major unsolved questions. And they fall under four main categories, which I touch on in different parts of the thesis. So first of all, just where do they come from? We know one way to make black holes, which is when a massive star, at least 30-ish times the mass of the Sun, goes supernova and leaves behind a remnant. So maybe the ones at the centers of galaxies got seeded, we say, in the same way. Perhaps the very first stars simply blew up and left behind what we call light seeds. Those should be pretty common. All you need is a single star to end its life. But by light, I mean only going up to maybe like 100 times the mass of the Sun. Alternatively, there's this direct collapse model, which Priya has worked a lot on. And in this picture, maybe there was this enormous primordial gas cloud up to like 100,000 times the mass of the Sun that directly collapsed under its own weight and went right into a black hole. And this is what we call a heavy seed. Those are thought to be rare because you need some special conditions to make this thing turn into a black hole instead of stars as it would normally. And yet this only gets you up to like 100,000 times the mass of the Sun. We've still got a long way to go to explain those things that are 10 billion times the mass of the Sun. The way that we think that black holes assemble most of their mass is by eating the gas from their galaxy. And this is an example of one in the process of doing so. This is Centaurus A, what's called an example of an active galactic nucleus, or an AGN. And at the center of this galaxy, there's a growing black hole. We like to think of images like this. And as it's growing, as it's eating all this mass, whatever passes the event horizon just gets stuck inside. But a lot of it doesn't make it all the way in, and even as it's doing so, it heats up as it crashes into itself in that deep gravitational potential well. So when these black holes grow, they'll emit a lot of light, winds, and even jets, as you can see in this case. And so, two other questions that we'd like to probe is what is it that makes these black holes grow? What's so special about this galaxy in particular that's making it grow so much more efficiently, actually about 100,000 times more efficiently than the one at the center of M87 in terms of like its Eddington rate? And then finally, how do they affect their galaxies? So our current theoretical understanding is that, as you might guess from this picture, when these black holes are growing, even though they're so much less massive than the entire galaxy itself, they're powerful enough to sculpt the evolution of the gas content of these galaxies and potentially shut off star formation entirely. One of the ways we think that galaxies might transport gas to the centers and feed their black holes is when galaxies merge. So this is going to happen to our own galaxy, the Milky Way, in about 4 billion years when it collides with the Andromeda galaxy. And when that happens, these two nice spiral arms are going to get totally disrupted like this. The gas crashes into itself and then gets funneled toward the center in this way. And there are many idealized simulations that show that kind of behavior. And one thing that we're not sure about, though, is that if both of these things started off with black holes at their centers, when is it that they're actually going to merge together? This galaxy merged with another one. Are the black holes at the centers going to merge as well? We think probably, but maybe not all of them, especially not the most extreme mass ratios. And so, in my thesis, which is comprised of three different topics, 5 different papers, we touch on many of these questions with a variety of techniques. So first I'm going to talk about these special kinds of flares around a black hole binary with ballistic simulations that I did. And then we zoom out and talk about the black hole galaxy connection. And there are 2 ways in which I've done this with the thesis. So one way is a cosmological simulation. I analyzed the Romulus simulations run by Michael Tremmel. And the other technique, which I use more, is called semi-analytic modeling, which is a quicker and a faster way to model those black hole evolution, but you have to make a bunch more assumptions. So first, let's talk about those special flares. You may have heard that around a black hole, gravity can be changing so quickly that the gravity at your feet would be stronger than that at your head, and you get torn apart. And this is what's called spaghettification. Actually, this doesn't usually happen around the supermassive ones for a human, because the tides are more gentle, but around like a stellar mass black hole. And the thing is, this doesn't just happen to fictional astronauts, it can also happen to stars. And we've observed that happening. So in the past 10-20 years, this has been a blooming new field. A tidal disruption event, also called a TDE, is a flare from the spaghettification and consumption of a star. And here, this is a simulation not run by me, but by someone named James Guichon. There's a star that's about to get ripped up there and a black hole. And when it does, it gets torn apart into the stream. Half of it is unbound, flies off into space. The other half gradually drains onto the black hole. And it turns out that you can easily derive on the back of an envelope, as theorists like to say, this nice equation for the evolution of that flare. M dot black hole goes as t to the minus 5/3. And for family, when you put a dot on something, that means you're taking a time derivative. So the rate of change of the mass of this black hole follows that law, and it actually translates pretty nicely into the shape of the X-ray flare. And so we know about a few dozen of these. But TDEs aren't actually significant for black hole growth. This only happens once every 100,000 years for a galaxy like our own. So it may not be totally obvious why you should care about these. But one of the reasons is that for most of these simulations where you're trying to understand black hole growth, you don't actually know where to start your simulation, what those boundary conditions should be. This is a nice case where you actually know, well, we know stars a lot better than black holes. You could start off with a star with some profile and just let that evolve. You can also light up otherwise hidden black holes that aren't turned on in the normal way as an AGN, whatever normal even means, we're not sure yet. And they also just are convenient because they evolve on human timescales. A flare like that is going to last a few years, meaning you can spend a career watching a few of them, publishing papers, and then learning something for your next proposals. And for us, we were interested not in a normal case, but what about black hole binaries? The thing is that the timescales work out that you would be able to probe binary black holes on length scales that are about to enter the gravitational wave regime. So they would potentially merge soon and would be candidates for things that we would be able to see with gravitational wave instruments in the future. And there's actually already one binary TDE candidate, although people aren't completely convinced. So the idea is we will just simulate the evolution of star particles in a gravitational field that's comprised of these two black holes. I split up the star into 100,000 particles and just integrate the gravity. So basically just solve the three-body problem for each of the pieces of the star. Not a normal one. I put in weird post-Newtonian potentials so to take into account general relativistic effects. But that was the idea. And we wanted to see if we could understand how this flare would be different from the one you saw before, where you just have a single stream that extends and gradually drains, maintaining the same general structure. And the output was basically a bunch of fun movies. So here's one example. We've got two in the plane. This is two black holes. There's a bunch of particles stacked on top of each other right now. That's the star that's red at the very... It's a little bit offset from that more massive black hole. As this evolves, you're going to see a stream come out. I've color-coded them according to energy. So the least bound things are going to fly off. Those are going to be red. The most bound are purple. They're going to get sucked in really quickly, or you'll probably miss them. And so this happens, and the binary is going around. Okay, there was a weird jumping. And now when the secondary black hole comes in, now it's a total mess. You've got an enormous, large-scale structure. Maybe that has implications for the reprocessing of the TDE into the optical wavelengths. So yeah, as this keeps going around, we first had this weird jumping thing, and then the secondary black hole comes in and makes a whole mess every time it does so. And you can actually if you keep track of all of the particles in the simulation, you can reconstruct the mass fallback rate onto these black holes, which might translate into the accretion rates. So here on the right, I'm now plotting the rate at which mass is falling onto the primary black hole in blue, the secondary in green. That analytic prediction, that equation that I showed before, is that dashed red line, and TDEs in the X-ray tend to follow that. Okay, and so you'll notice at the beginning, it's still following that pretty normally, but then something strange starts to happen. So first, there's this thing that we call truncation, and that actually happens when some material misses. That's what that weird jumping stuff was. So it misses the first black hole, and then it comes in later. That's why there's this extra stuff now over here. And then later on when the secondary comes by, now there are some gaps in the stream because all the stuff that would have otherwise fallen onto that primary black hole is just all over the place now. So the takeaway is that you have this truncation here, and it's a bit of a mess, but you'll pick up this periodic signal. So this is the period over which the binary completes one orbit. So if we're lucky and we see those would be good candidates for a binary black hole evolving on timescales comparable to the flare. By the way, those separations are milliparsecs, forgot to say. 1 parsec being 3.26 light years. And for reference, the distance to Pluto is 0.15 milliparsecs. So this is kind of between solar system and stellar scales. Here's a fun special case. This is what we call stream trading. So I've put these two massive black holes in the gravitational regime already. This is already at 0.1 milliparsecs. And as the stream falls in, it's first accreting onto the first one, and then now the second one has taken over ownership of the stream, and then it keeps evolving like that. And now you're changing from accreting onto the first one, then the second one, and then the first one and the second one. You get this weird scallop thing. If that actually translates into a light curve, which is a big if, then you would pick up that periodic signal as well, and maybe some oscillating spectroscopic signatures. Okay, so that's it for that special flare. We're now going to zoom out to intergalactic scales. I'm usually more interested in the connection between black holes and their galaxies. And we were at milliparsec before. The separations between galaxies are typically actually megaparsecs. And so we're zooming out by a factor of 10 to the 9. Now, you can't do the same sort of techniques that I did before, splitting up a star into a bunch of particles, because that would just take way too long. You need to use different techniques. So the question we're trying to answer in particular is how galaxies and their black holes co-evolve. This is a figure from Marta Voluntari, 2012. We've got on the x-axis the mass of the galaxy, and on the y-axis the mass of the black hole. And is it the case that the black hole grows first and then the galaxy catches up? Or the galaxy grows first and then the black hole catches up, or somewhere in between? And does that depend on the mass of the galaxy and the environment? We still don't have a complete understanding of this. And by the way, you can actually look literally back in time in astronomy. The reason is that light has a finite speed, and so we can actually directly look into the past by looking at things that are redshifted. We look at galaxies where it's taken the light billions of years to get to us, and then we know how that galaxy was billions of years ago. The redshift of the galaxy tells us when that was, because light is traveling through expanding space, therefore the light is expanding as well, and expanded light gets redder. On the theoretical side, one of the best ways to study the change of stuff over cosmological timescales is to run what's called a cosmological simulation. This is a single galaxy in the Romulus simulations, run by Michael Tremmel. He was kind enough to send me this video. This is the assembly of just a single galaxy, and gas temperature is shown. So there's a galaxy forming in the middle, and as it accretes stuff, stars and black holes are heating up the gas to higher temperatures. And you'll see on the bottom left, since we've zoomed out so much, the resolution of a simulation like this, and this is state-of-the-art, is going to be like a couple hundred parsecs, also a couple hundred-ish light years as well. And an individual particle of gas or stars is now actually not just one star, but 100,000 stars. So you need to make approximations to try and do the physics on even smaller scales. And in terms of the black hole galaxy connection, the main result from this work was the fact that black holes and their galaxies assemble in tandem. So this is a science plot plotting the rate of change of the black hole mass, so the black hole accretion rate, versus the rate of change of the galaxy's mass. This is the star formation rate. And each of these panels is a different redshift, so a different epoch in time. And what you'll see for each of these data points, each of which represents a galaxy in the simulation, is a nice linear correlation independent of the redshift. And it actually matches this gray band, which was what was observed by stacking a bunch of star-forming galaxies and X-rays, which picks out black hole accretion. Not only that, but it doesn't depend on redshift, it also doesn't depend on stellar mass or even the intergalactic environment. You make the same plot for a galaxy cluster, it actually looks the same. And so the takeaway is that on long timescales, black hole growth follows the star formation. If you add in a few more free parameters, you can even explain up to 70% of all of the black hole growth variations. The other parameters being the black hole galaxy mass ratio, which I've color-coded by here, and also the cold gas fraction. And so, from before, now this is black hole mass versus stellar mass, as in that cartoon. If in the very early universe, we've actually got massive black holes compared to their galaxies, mostly because of just resolution, but they don't overgrow. So these galaxies need to catch up until you reach this critical ratio, and then black holes and their galaxies grow in tandem along a 45-degree angle here, until maybe sometimes in the late universe, some are going vertically because the galaxies have quenched, and sometimes they get stripped of stars and go a bit that way as well. And so returning to this picture, how do black holes and their galaxies co-evolve? At least in the Romulus simulations, it appears that symbiosis is the answer. But don't take away that like we've actually completely solved this problem or anything. This is just one simulation, and when we go to conferences, we need to compare with people who've made all sorts of different approximations and see what things are actually constant, what things might just be artifacts, and stuff like that. A simulation like Romulus takes months or years to run, and years more to even understand their outputs fully. So an alternative approach to trying to model this is called a semi-analytic model, or a SAM. So the idea is you boil down the universe to a set of equations that you could write down on a piece of paper. You don't just take a whole bunch of gas, a star, and dark matter particles and just let it do whatever it wants. You make some hypotheses. That's what those equations are. But if you can write them down, all you got to do is some math. And you'll output a bunch of nice things that you can compare to the observations. In particular, these black hole host relations and luminosity functions, which I'll get to. You can also do things that haven't been detected yet, like gravitational waves from supermassive black holes. So one realization of the universe takes me a few hours. And that means we can test a whole bunch of different assumptions and see what we can learn. To give you a better idea, say that we want to understand the evolution of this beautifully depicted host galaxy. There's a black hole in the middle. This is the present day. Now, under the assumption that black holes and their galaxies co-evolve in some way, in order to understand the growth of the black hole in this galaxy, I need to know how that galaxy assembled. So I'm going to split this up and go back in time to generate a merger tree. These are all of the pieces of stuff that eventually merged together to form that galaxy at the present day. And then, since I'm interested in black holes, next step is just seed them somehow. And like I mentioned before, there are a couple options that we try. There are a bunch more in the literature. And then, now that we're armed with a bunch of equations and initial conditions, you just integrate forward. At every time step, integrate our prescriptions for black hole growth. And our assumption is that when galaxies merge together, the black holes are going to turn on, and they may also cause black hole mergers as well. So you just keep doing this for personally 820 time steps down to the present day. But then you got to do this for a bunch of different environments. So this was just one galaxy of a given mass. Galaxies also live in much more massive halos, much more busier environments. And then you weight them by the abundances of all of these different environments, and you've got a realistic sample of the universe. And if you're a really good programmer, you can get your SAM to talk to you and be your friend. So I was tired of checking on whether my calculations were actually done yet. So I got it to send me these emails and tell me how long it took, and give me a bit of encouragement in the winter months when it's so dark. All right, and so once you've done something like this, you want to compare to the actual observables to see how you did. So at redshift 0, at the present day, local relations are a sort of boundary condition. This is where you want to land at the present. So here's a really famous one. This is called the M-sigma relation. It relates the mass of the black hole to the gravitational potential. Sigma actually equals how quickly the stars are moving inside of the galaxies. And the faster that stars are moving, the stronger the gravitational potential is. Not just like immediately around the black hole, but even on scales where the black hole isn't actually dominating the potential. Otherwise, that would be pretty tautological. And you can see this nice relation that has a scatter of about 0.3 dex. The other really important observable is luminosity functions. And that tells us how the population evolves. So say we're at a fixed snapshot in time, and these are a bunch of black holes that are growing. In this cartoon, the white things are bright and the red things are faint. And what people like to do is to gather these up, put the faint things together and the bright things together and make a histogram. And this is what we call the luminosity function. And by probing how much black holes are shining, that actually directly tells us how quickly they're growing. Because a faster growing black hole shines proportionally brighter. If more stuff is falling into it, there's more gas to shine. And so we like to replace that luminosity down there with the growth rate. And so there's still some freedom in terms of assigning those growth rates to black holes and those black holes to galaxies. So just matching those two things isn't, well, it's not completely straightforward to just match those. So this is just one example of a thing that you could do. These are luminosity functions that go out to redshift of 6. 6 is about 1 billion years since the beginning of the universe. And black is real data, which we're trying to match with this model, which is in blue. And we've made the hypothesis, galaxy mergers make black holes grow at maximum efficiency at the Eddington limit for the astronomers until they reach some cap that we've prescribed. And so the idea is to try and see how well the blue matches the black. It actually does pretty good for redshift 6 down to 2, but then something needs to change. After all, we know that locally not all black holes are growing at that maximum Eddington limit. And so that's telling us that those simple assumptions are good enough for the early universe, but not afterwards. And you could also push past this current observational limit at redshift of 6 to make predictions for the next generations of telescopes. So one thing that we're particularly interested in is trying to distinguish these light seeds from the heavy seeds. And we wrote a paper about various ways to do that with different kinds of observables. And one thing you could do is go past redshift 6, now we're going out to 12. There are now 4 different curves. The red and the orange go together, as do the purple and blue. Those are the light versus the heavy seeds. And you can see that at redshift 6, everything is basically on top of each other, at least where we can observe. But if you go far enough in redshift, those 2 sets of curves start to diverge. So if we focus on redshift 10, for example, there are more things at low luminosity for the light seeds. Basically, those are assumed to be common, and so the direct consequence is that there are more of them that are able to shine. Whereas for the heavy seeds, they started off with more mass, and that means that they're able to grow faster and will also be shining more brightly for that reason. And so this tells us that if we can make new telescopes that can actually see redshift 10, we'll be able to distinguish these seeding models. One example of one has its point source sensitivity shown as this dashed blue line that's Lynx. And now that abundance, you can actually break degeneracies there by looking at lower redshift as well, something we call the local occupation fraction of black holes. This is a plot of the fraction of galaxies of a given stellar mass that actually have a black hole of at least this mass. The data is shown in black. It doesn't actually completely agree with each other. You got to make a bunch of assumptions in order to put things on a plot like this. And our model is the blue rectangles, and you can see that you can distinguish the light versus heavy seeds based on these plots. They don't all look the same, and so finding black holes in dwarf galaxies at redshift 0 will help us constrain seeding models as well. And one of the advantages of a semi-analytic model is that that's directly related to the occupation fraction, even way out at redshift 10. Since we've done it self-consistently. Finally, another way to distinguish these seeds is via gravitational waves. So fully explaining what those are is an entirely different talk. But when 2 massive compact objects, such as black holes, merge together, they cause ripples in the fabric of space-time. And a few years ago, the LIGO collaboration was the first to report successful detections of these. In the future, there's going to be a gravitational wave detector in space. This is going to be called LISA, and people are interested in seeing if we can distinguish different models for seeding using those gravitational waves. It's going to be much higher mass than you can probe on the ground. And so here, the 2 sets of curves are a lot different right there. That's at 1,000 times the mass of the sun. This is actually the number of events that you can see after 4 years of doing that gravitational wave mission. And so gravitational waves will reveal populations that our telescopes can't. Merging black holes don't actually need to be turned on in any way that is growing and shining. So it'll be interesting trying to put all of this together and seeing what we can learn in the next few decades. Alright, so in conclusion, we can study supermassive black holes by how their gravity affects the surroundings, by causing gas to heat up and shine, and also by the gravitational waves that they'll emit when they merge. We can understand these tidal disruption events from binary black holes that are near merger using these ballistic simulations. People, by the way, have followed up on that using hydrodynamical simulations with a few cases. You can't, obviously that takes longer, so you need to restrict yourself in some way. But they find that many of those results stand up. In the Romulus cosmological simulations, seems like black holes in their galaxies just grow in tandem. And we can identify signatures of black hole seeding models with next generation telescopes and gravitational waves. Up next, I'm going to Harvard, and I'm going to be spending some time working on the Event Horizon Telescope. That's that collaboration that took that image of M87 star, that black hole. And one thing that I'm thinking about is the time variability. So you can see even in these image reconstructions on different days, if you look really closely, that these images don't look exactly the same. It's more convincing in visibility space, which is what they actually observed. But yeah, they still haven't quantified that and really tried to get everything that they can out of the data. So the semi-analytic models can be further refined. There's a wealth of observational data that is available that I still haven't fully incorporated into the model. And in Romulus, there are special cases of black hole evolution that I would like to look into. So ram pressure is one example. That's a galaxy that is experiencing a headwind as it's moving through a really dense environment. And it turns out that people have observed black holes grow more efficiently when that happens. We don't have an understanding of why that would be the case. Also working on characterizing populations of wandering black holes that are not near the centers of their galaxies. This was actually a project started by Charlotte Zimmer, who's in the audience here. So none of this would be possible without the support of many kind and wise scientists, especially, of course, my own advisor, Priya Natarajan. She's been pushing me and supporting me this entire time, and it's been a real pleasure to be working in your research group. Now, Michael did the heroic task of running the Romulus simulations and worked very closely with me to really figure out what they mean. Nico Cappelluti was really instrumental in a project I didn't have time to talk about on the clustering of black holes that we can't see yet. And there's a large group of people who have been supporting me throughout my scientific career. So one is Meredith Hughes here. She works on debris disks, and she's currently at Wesleyan. And yeah, if you're an exoplanet person, you might be surprised to see her there. But we were both at Berkeley when I was an undergrad, and she got me from not knowing how to open a terminal to first author paper in 2 years. She worked extremely closely. We met like 3 times a week, answered emails a lot. So she really jump-started me very well. And then I started working with Jason Dexter, who introduced me to the Event Horizon Telescope. Jane Dye worked with us doing the tidal disruption event paper. Fabio Picucci also did stuff with the clustering that I didn't have time to talk about. And I also worked with Meg Urey and her then postdoc Steph Lamassa on an observational project about red quasars. So black holes that are growing really quickly but are reddened by dust. And then finally, I'd really like to thank Michael Faison. I never did any scientific work with him, but he's the director of the Leitner Family Observatory and Planetarium, where I've spent a lot of time giving public talks and doing the planetarium shows. And yeah, I feel like I grew a lot in that area because of all the groundwork that he laid down and maintains. So that's sort of my academic family. My real family is significantly larger, by at least an order of magnitude. So this is a subset of my dad's side of the family. We met up for a family reunion last year in California. So I'm over there. In a Filipino family photo, I get to stand in the back.
Wow, very good.
My cousin Amanda's here somewhere.
Where are you,
Is she
Amanda?
here?
There you
Okay,
are.
yeah, there. And then, here's some more on my mom's side. Yeah, my parents are here today, as is my sister, my Aunt Melissa as well, and of course Sophie, my wonderful partner who's been supporting me even ever since the madness of quals even. I was even more stressed, way more stressed out about that than I was for my actual defense. But she kept me together while that was happening. And then, you know, I've got to thank the department at large and all of the faculty who make sure that we have a nice, welcoming environment. One thing that I noticed when visiting other schools was that, you know, there are a lot of places where people are a lot more standoffish, less comfortable talking to each other about anything aside from science. And I think we have a very nice community here. Thank you to all the friends who came out to support me a week ago here at ShareCon, and Daryl, who actually was there but didn't make it to the photo. So I got that. So yeah, it was a real pleasure to be here and work for the past 6 years. Doesn't feel like work really most of the time. Priya says she tells me to take time off, but when I'm not doing astronomy, I kind of feel that itch, and I really get excited. And she and the department as a whole really provide that environment for someone like me to thrive. So thank you all so much for coming. It's a real pleasure to see everybody in the same room like this. I'll take questions.